Alright, in this video we're looking at drawing derivatives. Now, if you hate algebra, it's your lucky day because we're basically not going to see any numbers in this video. It's all picture based. So first thing we're going to do for each of these functions is draw a sign diagram. Now, usually in exam questions and stuff, they won't give you actual numbers. They'll just label it as like A, B, C, D. So we'll do the same. First sign diagram is f of x. And just as a refresher, we put the x-intercepts on there. It's under the axis, then over the axis. Next sign diagram is f dash of x, and we put the stationary points on there. So that's B and D. So it goes positive slope, then it slopes down, then it slopes up. Next sign diagram, we put the inflection points on. Now, usually if this is an exam question, it will tell you that C is an inflection point, just to be extra sure. But we'll put C on there and we'll go minus and plus. Notice how I'm lining up the A's, B's, C's, and D's so that they're actually in the same spot correct with each other. It's very important. All right, next thing we're going to do is draw the derivatives. So draw f dash of x on top of the graph, and I've got this little handy table to help. When f has a point of inflection, f dash has a stationary point. So we expect to have a stationary point at C for f dash. So the actual picture of f dash will have a stationary point at C. F dash has x-intercepts whenever there were stationary points on f. So I'm going to take all the original stationary points, B and D, and I'm going to turn those into x-intercepts. Now, since we are sloping down, I expect my picture of f dash to go underneath because it will have negative values. I'm also supposed to hit a local minimum at C, a stationary point. So the derivative should look something like that in between C and D. So because the original graph is sloping down, that tells us that the graph of the derivative will go underneath the axis. Notice how it's sloping up after D. That'll tell us that the graph goes above the axis there. Notice how it's also sloping up before B. That'll tell us that the graph goes above the axis like that there. This graph here, the blue one, y equals f dash of x. Now, usually in an exam, they're not cruel enough to ask you to draw two derivatives on top, but we'll do it just for practice. Let's draw f double dash. So basically what this is going to do is, the easiest way to do it is spot the x-intercepts first. So f double dash will have an x-intercept whenever the original function has a point of inflection or whenever the derivative has a stationary point. So we've got this magic point here at C, where we've got a point of inflection there on f. We've got a stationary point on f dash. So our f double dash will have an x-intercept there. Now we look at the original function. It is concave down all three here. Very sad. That will mean the f dash will be in the negatives down here. It then becomes concave up after that. I'm very happy about that. So f double dash goes up after that. Now it turns out that f double dash is actually just going to be pretty much a straight line. Just like that. Y equals f dash dash of x. Now, what I really want to point out as well is you can actually sort of cheese drawing derivatives by calculating the turning points, mapping those out. So if I had a function, if I had a function here, which was f, and I count that it has 1, 2, 3 turning points, I would expect f dash to only have 2 turning points, and I'll expect f double dash to only have 1 turning point. And it kind of makes sense why that might be true, because if this was like x cubed plus all that stuff, your next term would be 3x squared, so it's only a quadratic. So that would have to be x4, and that would be x cubed, but same concept. And then the next one would be another degree lower, so you get 12x squared. So every time you do a derivative, you lose like a power on the x, and that's going to cause you to have one less turning point. This is almost true, but this is only a sometimes rule. It doesn't always work out like that, but it does if you're dealing with polynomials. Anyway, you can see it here because there's 2 turning points on the original function. F dash only had 1 turning point there, And then the f double dash had no turning points. It was straight. Cool. All right. Now, that's good. You can actually use these pluses and minuses to tell f dash was above, then below, then above the axis, and f double dash was below, then above the axis. And I've prepared this in advance on Desmos, and there's the original function. On Desmos, you can actually just hit this. You can type d by dx and then type in the original function. That'll do the derivative. There it is. And then here we go. That's the other one. So your pictures don't have to be perfect, but they should roughly resemble what it looks like. This one here. So let's do sign diagrams of everything. So here's x and f of x. We got to put our x-intercepts on, which there's none. So it's above the axis the whole time. Here we have x and f dash of x. We got to put our turning points on. There seems to be one at b and d. So we're going to do that. B and d. It slopes up, then down, then up. Here is x with f double dash of x. We got to put our points of inflection on here. So these will be at A, which I've marked, and C, which I've marked. Just a reminder, the exam questions will often tell you that they're points of inflection in the text. It is a happy face, then it's a sad face, then it's a happy face. So I've got to go plus, minus, plus. All right, wonderful. Now let's draw our derivatives on top. So for the original function, let's make sure we get our x-intercepts first. If I want f dash to have an x-intercept, the original function would have had a stationary point there. So let's put that in. So the two stationary points here, b and d, will become x-intercepts. I'm sloping down, which means the f dash will be underneath the graph. You can also tell this from the sign diagram how it goes minus in there. But at any rate, we're going to be dropping down and back up. Notice that I've very strategically, or maybe messed up the drawing a little bit, but very strategically made sure that the local minimum happens where the point of inflection happens. Because if f has a point of inflection, the derivative has to have a stationary point when you draw it. That's why. Speaking of, we got another point of inflection up here. So this point of inflection A needs to become a stationary point. And I reckon that's going to be a local maximum. Cool. Now this function's getting flat, so like the slope approximately equals 0 there. Or in other words, f dash of x is the slope. That should roughly equal 0. So this function here is actually going to level back out. Going to zoom towards 0 there on the slope. On the other side, it's getting very steep. So the slope's going to get more and more positive. All right, now let's draw our next derivative down. So if we do that, let's see, any inflection points on the original graph should become x-intercepts. So A and C will become x-intercepts. We said we were happy here, which means we're above. We said we were sad here, which means we're below. And then we're happy at the end, which means we're above. So pretty much what's going to happen is, let's deal with this middle bit first. Note that I've now basically got an inflection point somewhere along the graph here. Next derivative down, if I've got an inflection point here on f dash, it's going to have a stationary point on f double dash. So that means that I'm looking to have a local minimum, not necessarily at B, because that's the x-intercept that I've marked there, but somewhere here. Local minimum, zoom back up through C. All right, good. We've lost half the derivative. Cool. All right, now let's see what's going to happen after this. So basically we're a happy face that's getting even happier. So we're just going to go up. Y equals f double dash of x. Now I don't know exactly how these are all going to cross over with each other there, but usually that doesn't really matter too much with these questions. It matters that you get the right shape. All right, now let's look at what's happening to, I guess the slope of this graph is also reaching 0. So that would tell me something about what's happening with the green one. I've also got another inflection point there. So that's going to translate into being a local maximum there. And it looks to me like maybe this green one's going to settle down at 0 as well. Because if you look at the slope of the blue line, so slope of f dash should tell you about the height of f double dash. Because basically, to go down one derivative is that process. So yeah, like how when we were drawing f dash, we used the slope of the original function to do it. That works even if you're going from f dash to f double dash, that same trick. Anyway, so the green line should level out, and let's see if our Desmos graph seems to match what we got here. So there it is, I prepared it earlier. You can do ddx to differentiate it, there it is. You can do that one there, which seems to match pretty well what we've got. Just a couple things to mention at the end here. So you might notice on Desmos that the blue graph doesn't go above the red graph, but that doesn't really matter because all the right features are in the right places. You've got the stationary point there with the inflection point on the red and the x-intercept on the green. So as long as you're matching that, inflection, stationary, x-intercept, then you should be okay. The other thing that I will mention is I have been checking these on Desmos because I wrote the questions and I know what the equations were. You will not have the equation in like an exam question. So you just have to do this by feel. Unfortunately, there's not a great way to double check it.